Welcome to The Explainer. Let's jump right in, because today we're tackling the absolute core challenge of modern generative AI. You see, we're living through this massive software paradigm shift right now. Large language models are, frankly, incredibly powerful, but they share one critical flaw. They are completely frozen in time. A model trained on the public internet last year has absolutely no insight into your private corporate data, your latest customer support logs, or your proprietary code base.
So picture this. You've got the most powerful reasoning engine in human history at your fingertips, but it's effectively an amnesia. It desperately needs a system to retrieve specific proprietary facts. And here's the kicker. It needs to do it in under 50 milliseconds, so the user doesn't even realize the AI is furiously looking things up behind the scenes.
Okay, let's dive into this. The industry's elegant solution to this amnesia problem is Retrieval-Augmented Generation, or RAG. Instead of burning millions of dollars retraining a model, which, let's be honest, is incredibly slow and expensive, we just fetch the exact relevant information and inject it directly into the model's prompt right at runtime. The model then synthesizes that retrieved context into a perfect, up-to-date answer.
Here's our roadmap for today. We're going to look at the AI memory bottleneck, the math of similarity, FAISS index zoo, the document chunking dilemma, and lastly, building production pipelines.
All right, first up, Section 1, the AI memory bottleneck, building the pipeline.
So how does data actually flow into this engine? A RAG pipeline is split into two distinct workflows. First up is the offline ingestion loop. This is where you load your raw data, chunk it into smaller pieces, pass it through an embedding model to turn the text into mathematical vectors, and then index it into FAISS. Then you have the runtime inference loop. A user asks a question, we embed that query, and FAISS performs a similarity search to find the nearest mathematical neighbors. This is really where the magic happens. FAISS acts as this sublinear mathematical bridge, making it possible to search millions of mind-bending 1536-dimensional vectors in mere milliseconds, instead of painfully scanning them one by one.
Now, quick insider tip here from the source material. Watch out for this developer trap. FAISS strictly expects your vector data to be in 32-bit floats. But Python's NumPy library, well, it often defaults to 64-bit floats. If you don't explicitly cast this, you're going to feed float64 data into FAISS, it'll throw a super cryptic type error complaining about descriptors, and your whole pipeline will just crash. You absolutely must explicitly cast your data to float32 using NumPy before you interact with the library. Trust me on that one.
Moving right along to Section 2, the math of similarity, calculating distance.
Ever wonder how a database actually knows that the word cat is mathematically closer to kitten than it is to car in a high-dimensional hyperspace? Well, it all comes down to distance metrics, and your choice here has to perfectly align with how your embedding model was trained. Euclidean distance measures straight-line distance. It's highly sensitive to vector magnitude, which makes it great for computer vision. Inner product is essentially a dot product, super useful for recommendation systems where magnitude equals popularity. But for NLP and semantic search, cosine similarity is the industry standard. It isolates the angular relationship between two vectors and completely ignores their absolute length. That allows it to focus purely on the core semantic meaning of the text.
But here's the catch, and it's a big one that trips up a lot of developers. Now, what's really interesting about this is that FAISS doesn't actually have a cosine similarity flag. No way. It's literally not in the library. To achieve cosine similarity, you must first apply L2 normalization to project your vectors onto a unit hypersphere, making their length exactly 1. Once they're normalized, an inner product calculation becomes mathematically identical to cosine similarity. Workaround achieved.
Let's look under the hood. Section 3, FAISS, the index zoo.
FAISS isn't just one single algorithm. It's a whole collection of data structures designed to optimize search speed, memory, and accuracy. And choosing your index is all about trade-offs. The flat index is pure brute force. It compares your query to every single vector. Sure, it guarantees 100% accuracy, but it's agonizingly slow at scale. On the absolute other extreme, HNSW organizes vectors into a multi-layered navigational graph. It's blisteringly fast and highly accurate, but man, it consumes massive amounts of RAM. For billion-scale datasets where memory is super tight, developers usually turn to IVFPQ. That compresses vectors down to tiny bit codes, sacrificing just a little bit of accuracy for incredible efficiency.
Now, if you're rolling with an inverted file index, or IFV, you've got to balance speed and recall by tweaking two key hyperparameters. At build time, NList uses clustering to divide your vector space into distinct zones, basically Voronoi cells.
At runtime, nprobe acts as your direct dial. It tells FAISS how many of those nearby zones to actually search. Turning it up increases your accuracy because you're checking more clusters, but naturally it slows down your query speed.
Okay, Section 4, the document chunking dilemma.
So, we've built the engine and tuned the structure. Now we need to look at the fuel powering it, how we actually slice up our documents. You might assume more complex is better, right? Well, the benchmark data reveals something super surprising. Basic recursive splitting, which just tries to keep paragraphs and sentences together up to 512 tokens, actually outperforms the highly expensive sophisticated methods. Semantic chunking tends to overfragment text into these tiny microchunks that completely lack context. And propositional chunking, it costs an absolute fortune in compute for worse retrieval accuracy. Sometimes, simple really is just better.
And this brilliantly illustrates one of the biggest headaches in RAG, the lost context problem. Naive chunking slices a document up before embedding it. Think about it. If chunk 1 says Berlin and chunk 2 says the city, chunk 2's vector has literally no idea what city it's referring to. Late chunking reverses this whole process. It embeds the entire document first, letting the transformer model's global self-attention mechanism map all those pronouns back to their original nouns. Only then does it mathematically pool the tokens into chunks.
Let's look at the actual numbers to prove it. Here we're querying for information about Berlin. The first sentence matches well in both methods as you'd expect, but look at the second and third sentences, the ones starting with its and the city. With naive chunking, similarity drops way down to roughly 0.70 and 0.75. But with late chunking, look at that jump, from a poor 0.70 straight up to a massive 0.82. It successfully remembered that the city means Berlin across the chunk boundaries. That is a real game changer.
Finally, bringing it all together. Section 5, building production pipelines. When you're actually deploying these systems, the research points out 3 major architectural pitfalls you absolutely have to avoid to keep things from blowing up. First, ID management. FAISS defaults to sequential IDs. If you delete a vector and add a new one in a mutable system, the internal math gets totally confused and can corrupt your entire index. Always wrap your index in an index ID map and supply your own database IDs. Second, be super careful saving and loading indexes across different CPU architectures. AVX2 compiler mismatches will break your search wrappers. Finally, if you're using a GPU index for those lightning-fast speeds, remember you cannot write it directly to disk. You've got to convert it back to a CPU index before saving.
So, bottom line, when should you use bare metal FAISS versus just paying for a managed vector database like Pinecone or Milvus? Well, FAISS is a library. It runs entirely in your RAM, it's totally free, and it offers extreme low latency with absolute data privacy. But doing updates and managing metadata is really tough. Managed vector DBs, on the other hand, are full systems. Yeah, you pay SaaS fees, but they handle dynamic data, horizontal scaling, and complex metadata filtering right out of the box.
So the crucial point to take away from all this is that mastering the generative AI model itself is really only half the battle. Mastering retrieval, the memory, is where the real competitive advantage lies in software today. We've walked through the math, the architecture, and the hidden traps of vector search directly from the source material. You now know exactly how to build an AI's long-term memory. The only question left is, what are you going to teach it first? Thanks for joining me for this explainer. Keep building, and we'll see you next time.